Hello, this is a problem from CPM Integrated Math 3 8-63, where if you are given pairs of numbers that are roots of a polynomial, write the equation of that second degree polynomial with these corresponding roots. So I like to combine these two things together, the -3, they are both -3. One is plus, the other is minus the square root of 2. I wanted to point out that these are real roots. Okay, again, and they are just irrational numbers. Irrational numbers are still real numbers. And this really comes from, we'll see when we end up rewriting this, that this just would not be a factorable equation. And so working backwards here, I would add the 3 to the other side as my first step. And then I would have x plus 3 equaling plus or minus the square root of 2. And then in order to figure out, well, what is the quadratic that would have these roots? If I square both sides and then simplify what I have left, I'm going to keep this as x plus 3 squared. And regardless if you have plus or minus, when you square anything, it will always be positive. And again, when you square a square root, it drops the square root. And so the squaring the square root of 2 just leaves you with a 2. Now again, continuing to rewrite this, I'm going to move the 2 to the other side. And so if I have then minus 2 equals 0, that would be how I figure out those particular roots. But I replaced the 0 with the y because in the end, if we're finding roots, we were figuring out when the output is equal to 0 because those are how you find any x-intercepts if they exist. So this is the vertex form of the equation, and it's fine to leave it in vertex form. But you might want to rewrite it in standard form. And so if I rewrite that in standard form, remember, that is the same thing as x plus 3 times x plus 3. And so part of that simplifies to being x squared plus 6x plus 9, and then we have the minus 2 equaling y. And so again, y equals x squared plus 6x plus 7. And you can see that, again, I had talked about earlier that this equation is not going to be factorable because you might think, well, 7 times 1 we'll multiply to 7 and add to 6. However, it's going to be a positive 7 times a negative 1 that would add to that positive 6x, but they would multiply times a negative. So this is not factorable. And if I think about what does this graph really look like, right? If this graph has a vertex, if I look at the vertex form at -3, -2, and what does that look like? And we can see why there are no real x-intercepts using our knowledge from chapter 2 when we graphed quadratics. Thinking about shift to the left 3, down 2, that would make the vertex right here at 3, -3, -2. And thinking about the parent graph here, 1 to the right, it would go up by 1. 1 to the left, it would go up by 1. 2 to the right, it would grow up by 1, 2, 3, 4. And same thing over here. And so if you notice, when I graph this, I think it's a lot more clear that this does have x-intercepts. There's an x-intercept right here and right here, but they're not integers, right? These are irrational numbers. And so we figured that out, that one of them is going to be the -3 plus the square root of 2, and the other one right here is the -3 minus the square root of 2. And we just figured out how do we start from these roots to work backwards to write the equation. For the very last problem on this problem 8-63, where they gave you only one real root, the one real root that they gave us for this problem on part E was x equals to 5. And so I could just say x equals 5. Working backwards, it must be x minus 5 that equaled 0. And again, if it's only one real root, you got to think about that it must bounce there, right? It's the same idea if we square both sides, just like we've been doing. It's x minus minus 5 squared, that would equal still 0, replacing the 0 with a y, because if we were finding roots, that's what we must have already done. So this is the quadratic that, again, as you know, it bounces off of the x-axis at that value of 5, leading to only one real root, and that would be at a value of 5. And so I hope that these videos have helped you to better understand how we work backwards from the real roots of a quadratic in order to write its equation.